So just a couple of announcements to get started. The first test, it's not right now, but it is coming up. So if you look on LMS, you can see it. But it's going to be in February. For B-Day, it'll be February 18th. But yeah, so that's not the right thing. So just keep that in mind. Still a few weeks away, but it is coming up. We finished up with chapter 14, all about mixtures and solutions and everything last time. The chapter 15 is basically thermodynamics, how heat moves through different things and calculating that. I've decided we're going to skip over chapter 15, not because you can't do it or it's too complicated or anything, but just I think that there are more interesting chapters. Chapter 15 is, it kind of goes back to you can't really touch and feel what's going on. I mean, obviously heat you can feel, but I don't know. It really is just a bunch of equations and things like that. So, like I said, I think there are some other things that are probably more interesting, and so we're going to save time for those. So we'll skip over chapter 15 and we'll actually go straight into chapter 16. Now, chapter 16 and even some of the other chapters, every once in a while they'll bring up a concept from chapter 15 that we skipped. When they do, we'll just explain it at that point, and that'll be how we get around that. So, anyway, chapter 16 it's titled Reaction Rates. And the fact is, different reactions happen at different rates. Some reactions happen very, very quickly. Other reactions go a little bit slower. And then, of course, there are some reactions that just go really, really slow. So, now, of course, fast and slow are not very precise. Fast is relative. You talk about a fast human being, well, they can run pretty quick, but the fastest human being, well, they're pretty darn slow compared to something like a car. And even within cars, you can have a really cheap small engine car, and then you can have super high-end sports cars. So fast is an inexact term, we'll say. Okay. So of course, we want it to be a little bit more exact, and we want to be able to compare things with numbers. Okay. So we need to bring in this idea of quantifying the speed. Now, quantifying speed really isn't that hard. We do it all the time. Anyone who's driving, they can look down at the instrument panel in the car, and it'll tell you, how fast is this car moving. Okay. Now, for moving something, it's the distance over time. Now, obviously, in chemical reactions, we're not going to be able to measure distance because while, sure, things are moving around in that reaction, they're all moving randomly and we can't really measure their movement anyway. But we do still want time. Okay? Now, of course, time isn't like a specific time. It's not like, oh, let me check what time it is. Okay? It's really the change in time, how long it took to go this distance, which we can represent as delta t. Use a lowercase t for time, because uppercase T normally talks about temperature. Anyway. And delta, we've used delta a few times recently. It means change. So when you see delta T, really all that we're talking about is how long of a time frame are we talking about? Is it 1 second? Is it 1 minute? Is it 1 day? Okay. Now SI units, time is typically measured in seconds. And so instead of saying 1 minute, you almost always say 60 seconds, but anyway. All you do, calculate how long it is. We got this. And then, since we're not measuring distance, now we are going to measure a change. And really, distance is just the change in position. Okay, so we're doing a change over how long. And for reactions, we're going to measure a specific quantity. And really, that quantity is how much of either a reactant or a product do we have. So we'll measure it at the beginning, and then we'll make another measurement, okay, to see how much that changed, divide it by how much the change in time was, how long we let this reaction go. And that will actually give us an average rate. So it's not instantaneous, it's an average rate. Just like, you know, if you go back to the driving example, if you say, okay, I started out at my house and I got to my destination. We'll say the destination was 15 kilometers away. Okay. So you did that 15 kilometers, and let's say it took you, well, 10 minutes. Okay. You would take the distance divided by the time. That would give you the average of your speed between where you started and where you finished. But obviously, you wouldn't be going that same speed the entire time. Okay? It'll go up and down, but that will give you the average. And that's what we're looking at right here, an average rate. So how do we measure quantity? Well, the easiest way to do it is, well, the easiest way to do it in liquid chemistry, which is what we often will talk about, and even this works a bit in other phases, but anyway, concentration. Like if we want to talk about molarity, okay? Molarity. You calculate what the concentration is at the beginning, what it is at the end, or at whatever point we measure again. Take that difference, divide it by the time difference. That gives us the average rate of this reaction. Okay? Otherwise, the reaction rate is what the book says. Okay? Um, reaction rate of a chemical reaction is the change in concentration of a reactant or a product per unit of time. So we get change in concentration. Okay. Now, usually, if we use molarity, okay, remember molarity is moles per liter. So we're going to have this unit on top, moles per liter. On the bottom, remember we're going to use seconds. So really our units, moles per liter seconds, is what we're looking at. Okay? So that's the unit that we're most often going to end up with once we do all of our algebra and things like that. Okay? So. When we write this as an official equation, I guess, in the book, okay? So we get our average reaction rate is equal to okay. We need a negative sign there. Okay. So we get the change in reactant. Now these brackets, we may have gone over this before, but just in case we haven't, anytime you see brackets like this squared off, that's telling you we want the concentration of whatever's in there. Okay? We want the concentration of whatever's in there. Now, we put this negative here because reactants, well, reactants are going away during a reaction. The reactants are what you start with. Okay? And so it should go down. Okay? And really that negative counteracts that because we do, anytime we do delta, we do final minus initial. So final is going to have less. And in order to counter out that negative, we put the negative there, and it gives us a positive rate. Anyway, we have that. So let's look at just an example, and it's really pretty straightforward. So we've got this example problem 1 on page 562. So we've got butyl chloride, C4H9Cl, and water. Okay. The concentration of the butyl chloride is 0.220 molar at the beginning. Okay. So our initial concentration is 0.220 molar. At 4 seconds, the concentration is 0.100 molar. So calculate the average reaction rate over the given time period. Okay. So remember, we do final minus initial. So we do, got this, negative 0.100 molar minus 0.220 molar. And it tells us that we did this measurement at 4 seconds. Now, if it doesn't tell you a different initial time, like it doesn't say at 2 seconds you measured and got this, and at 4 seconds you measured and got something else, just assume that your initial time was right at the beginning, which is times 0. So we take this and we put it into our equation. So we get negative, and that is negative 0.120 molar. And 4 minus 0 is 4. These negatives are going to cancel out. We just take that, divided by that, and that gives us our final answer of seconds, molarity per second, or moles per liter second. I don't care which one of those you write. The book usually will write moles per liter second. I don't care which one you write. So. But yeah, the average reaction rate, super easy. Okay, sometimes it goes faster, sometimes it goes slower, but whatever it is, we can calculate it using this. Now, what can change this? Well, we'll talk about some different things that can change this, but in order to really understand why they change it, we need to discuss something called collision theory. And collision theory is basically, in order to have two molecules or atoms or whatever you're dealing with, two things, react with each other, they have to run into each other. Okay? If you have two molecules on opposite sides of wherever you're doing the reaction, maybe it's a beaker, if they're on opposite sides, they're not going to react with each other because they can't interact. They can only react when they hit each other, when they collide. That's why we call it collision theory. Okay? And to go along with that, it makes it, there's a couple things. Not only do they have to collide in the right way. Okay? They have to collide with the right orientation. And it outlines a lot of this on 564 with pictures. I'm not going to draw all of them on the board, but it is there on page 564. So in this picture, we have collisions between carbon monoxide and nitrogen dioxide. Okay. And if we look at that equation, basically what's going to happen is the carbon monoxide is going to pull an oxygen off of the nitrogen dioxide. We're going to end up with carbon dioxide and nitrogen monoxide. Okay. So the first picture shows the carbon monoxide and the nitrogen dioxide coming together, but the two oxygens are hitting each other. Now the oxygen in the end has to attach itself onto the carbon. Okay? It doesn't attach itself to the other oxygen. And we can know this by writing out the Lewis structure. So if they collide into each other with both oxygens being what hit, well, that's not going to work because that oxygen isn't going to be able to attach to the other oxygen. So they just bounce off, no reaction. Okay. It's the same thing if the nitrogen in the nitrogen dioxide comes and hits the other molecule, because the nitrogen isn't going to be pulled away. That's just not the product that we're looking for. Okay, so if we line them up incorrectly again, that will bounce off. Okay, no reaction. But if we assume that we get everything lined up correctly, okay, we have the oxygen from the NO2 coming and hitting the carbon in the CO, what can happen is that oxygen is going to start to interact with the carbon, and all of a sudden the electrons in the bond between the nitrogen and the oxygen start to move out of the bond, and they start to create a new bond with the carbon. Okay? Now, for just a little while, both of those molecules are sort of stuck together. We call that an activated complex, where the molecules have run into each other in the right orientation, and they are in the process of switching over. Okay? And after they switch over, we get the products. Now, there is one other possibility. It's possible that we actually get these molecules to hit each other in the right orientation, but we still don't get a reaction because they didn't have enough energy. Okay? Every reaction out there has something that's called activation energy. And it's just the amount of energy that is needed to basically break the bonds in the existing molecules so that they can be reformed into the new ones. Now, activation energy varies quite a bit. There are a lot of reactions where just the heat in the room provides enough energy to start the reaction. There are other reactions that you have to put a whole lot of heat into in order to get them to do anything. Okay? Now, when we're talking about these things, we introduce the concept of an energy diagram. Okay? And energy diagrams let us know a lot about, well, the different energy levels of a bunch of different things. Okay? And when we look at energy diagrams, they can have different shapes and different looks, but really the way it works, okay, so over here on our y-axis, we have energy. You know, how much energy are we dealing with? And over here on our x-axis, it's just time, okay? How is the reaction going? Okay. The book actually calls it reaction progress, so we'll use that as well. Okay. And so you're going to have an energy level of your reactants, what you start with. You're going to see what the activation energy is. It is going to be a bump in the energy. And then you're going to see the energy level of the products. Okay. Now, in this example that we've been talking about, where you take the carbon monoxide plus the nitrogen dioxide, what that diagram looks like is a bit like that. Okay. So we can see the energy level of the reactants is higher than the energy level of the products. Okay. So if we take a dotted line here, okay, this difference, that is the amount of energy that is released when this reaction happens. Okay? How is that energy released? Well, it's in the form of heat. Okay? It's in the form of heat. When you do this reaction, it will actually feel warm to the touch. There are some chemical reactions that, as they progress, they get hot. Okay? Now, you may be familiar with these. You can get like hand warmers. You open them up. The iron reacts with oxygen in the air, and it heats up. Okay? There are other examples. A lot of military food use exothermic reactions. This is what we call an exothermic reaction. Exo meaning outside, and therm is temperature. So it's taking this energy, releasing it as heat into the environment. Okay. This right here, the measure of that is the activation energy. It's how much energy needs to be put into these things in order to get this reaction going. So it also could look something like this. Okay, where the reactants have a lower energy than the products. Okay. That's what we call endothermic, endo meaning inside. And these reactions get cold. So a lot of times in a first aid kit, you'll have like an instant ice pack. You break a barrier between two, well, they're really reactants. You break that barrier, allow them to mix, and when it forms a new compound, it has used more energy than it releases, which makes it get cold. Okay. So in this case, the activation energy is a whole lot more. Now, we didn't put any units here, so you can have these activation energies that look like they're really big, but can still, just the heat of the environment will provide that. Okay. And then, of course, this would be the energy that is absorbed, how much. Okay. Because yes, initially, it will absorb this much, but then it immediately releases that much out. So this is the difference. Okay. So exothermic means the energy is less in what we end with, our products, and that energy is released as heat. Endothermic means it has to basically, it takes energy out. Okay. Now, it does talk about spontaneity. Basically, that's what we're talking about is under certain conditions, will the reaction just happen, or do you need to put a little bit of energy into it? Okay. It uses a concept called delta G, which was talked about in chapter 15. Really, we don't need to get into the mechanics of delta G, but if delta G is a negative number, then it is spontaneous. If delta G is given to you and it's a negative number, it's a spontaneous reaction. If it's a positive, then once again, under those conditions, it's not spontaneous. So an example of a not spontaneous reaction is honestly one that we've talked about quite a bit. What's that? You can take a balloon, you can put hydrogen gas and oxygen gas together in the balloon, and they're just going to sit. Okay? Not going to do anything. But once we give this just a little bit of energy, okay? Now this is an exothermic reaction. So if we can give it a little bit of energy, it basically starts a chain reaction because all of this heat can be used for the next set of molecules. Okay, there's enough heat here to make this happen again over and over and over. So we give it a little bit of a kickstart, and then it happens very rapidly. Okay, but under these conditions, okay, whatever the conditions of putting it in the balloon, the delta G would have been positive, not spontaneous. We need to give it a little something. Okay, but once we give it that something, the conditions change, and then the rest of it becomes spontaneous. So, anyway, now there are some other factors that we need to discuss that can change reaction rates. Okay. Now these might sound a little bit familiar because the list is very similar to things that affect solvation. Okay. So now the first one is the nature of the reactants. Some things just react faster. That's just the way that they, the way they're set up with their electron shells and things like that. Some things just react faster. And there's nothing you can do to change it. It's part of their nature. Okay. Other things that we can change, concentration. Okay. If you increase the concentration of your reactants, well, there's more of them, which means you're going to get more collisions. If you have more collisions, it's going to happen faster. Okay. So increasing concentration is going to basically increase the rate. Okay. Once again, surface area, anything that has to make collisions is going to, if you have more surface area, you can get more collisions. Temperature. Most of the time, increasing temperature is going to increase the reaction rate. Not all the time. We will discuss some instances where it can actually inhibit rather than help, but mostly that's going to be in the next chapter. Okay. But yeah, so typically raising the temperature makes a big difference. So, and then we've got these things called catalysts. Now, catalysts are a unique group of things, And what they do is they speed up reactions, but they are not consumed by the reaction. Okay? So the catalyst, however much catalyst you put in at the beginning, you have that much catalyst at the end. And it speeds up a reaction, and often it can make a reaction that wouldn't normally happen. There are a lot of biological catalysts. Normally, we call them enzymes. Okay? They can make reactions that, if you just mix these things together, the activation energy is too high. But a catalyst, the way it works is it lowers the activation energy. Okay? It can do that in several different ways. Enzymes often lower the activation energy by holding things in the right position, which makes it so that they can react where they wouldn't normally. So anytime you have a catalyst, it basically changes your energy diagram to look more like that. Have a lower activation energy. Doesn't change how much you get, it just changes how fast it happens. Now, the opposite can be true too. We can have inhibitors. Inhibitors slow down. Okay. Sometimes they slow it down so much that it doesn't happen at all. Okay. Some inhibitors can raise the activation energy, making it harder for it to happen. In a biological system, inhibitors can interact with an enzyme, which remember is a catalyst, and the inhibitor will interact with the enzyme instead of the reactants. And so it can't do, the reactants can't interact with it and, create anything. One example, so if you're familiar with, car engines, modern car engines have something called a catalytic converter on them. It helps reduce harmful emissions out the tailpipe from incomplete combustion and things like that. The catalytic converter is actually a very, very expensive piece to replace on a car because it uses two expensive metals, rhodium and platinum. So you really don't want to hear your mechanic say that you need to replace your catalytic converter, because it's just a lot of money to replace. But luckily, remember, catalysts don't get used up. So it's not like you have to, every time you fill up gas, refill your catalytic converter. They just stay there. If your catalytic converter is not working, it's not because it's out of the catalyst, it's because something else is going on. So, also, the book does give a couple of terms here. The heterogeneous catalyst, remember, heterogeneous means not the same throughout. So the catalytic converter would be an example of a heterogeneous catalyst, because you've got the solid metals and the gases that it's interacting with. Okay? They're not in the same phase. Whereas a homogeneous catalyst is in the same phase or the same state of matter as what it's interacting with. So anyway. So that's where we're going to stop. Next time we'll get into reaction rate laws and things like that. And decided that I'm not going to assign homework today. Give a little break from homework. So if you have any homework that you haven't finished, use the time you would have for this assignment to finish it. But yeah, no homework today. And that's everything. So unless you have questions, we'll stop there.